But as a review, actually, let's talk about what we talked about last, or I guess 2 weeks ago, since last week we did not have class. We finished our discussion about converting numbers. We not only discussed converting to other various number systems, like for example, from decimal to octal, and then decimal to hexadecimal. Octal is base 8, hexadecimal is base 16. We also discussed converting between binary to octal and binary to hexadecimal. We talked about a couple of shortcuts for this. And we concluded with just talking about potential applications for this, because you guys have learned these wonderful number systems now, decimal, binary, octal, and hexadecimal, but you don't know how to apply it. And today we're going to start talking about the applications of all of this math. So I was able to kind of talk about this, kind of start this, but we unfortunately ran out of time. So let's go into this in a little bit more detail. So why are these number systems so important? Let's talk about some vocabulary words. A bit. So a bit is actually, a bit just means a binary digit. So that is the shorthand term, binary digit, same thing as bit. So bit is just a concatenation / abbreviation of binary digit. It's a computer's version of an atom. When you guys think of atom, I don't know if you guys have taken chemistry yet or not, but in chemistry, when we think about atom, it is the building block of all things in this universe. So a computer's version of an atom. When we think of atom, it's the building block of all things being able to be calculated or computed using a computer. So building block of computation. It is the smallest unit of storage, just like an atom. An atom is like the smallest unit of matter, or smallest independent unit of matter. Just like that, the bit is the smallest unit of storage. It can hold either a 0 or a 1, which is very, well, which is fair, to be honest, because a binary digit can only be a 0 or a 1, as a binary digit can be one of two numbers, because binary is base 2. So this so far hopefully isn't too bad. Now, a bit is very small. Literally can only be a 0 or a 1. As you start to combine bits together, group them and make them into larger units of storage, we have something called a byte. A byte is a grouping of 8 bits. So instead of a bit, which is just a 1, where you have 0 or 1, a byte would be 1, 2, 3, 4, 5, 6, 7, 8 bits all together. So this would be 1 byte, where each bit can be a 0 or a 1. With bytes, you have more possibilities. You have more flexibility in terms of what kind of data you want to store. So a byte can represent a number, a letter, a program instruction, part of an image, pretty much anything that can be represented as data. So in this case right here, when we have this number, we have 1, 2, 3, 4, 5, 6, 7, 8 bits. This is an example of 1 byte. And in fact, another word for a grouping of 8 bits is an address. The address. The address is not necessarily the same thing as a byte. A byte is like a unit of storage, and an address is a little bit different. An address is literally what it sounds like. It tells you the location of a specific part of data. So an address is also represented as 8 bits. So 1 byte is 8 bits, an address is 8 bits. A byte is typically representative of a unit of storage, whereas an address normally represents where your data is being stored. As you have more and more data, so bigger sets of data, you typically want to use different units, different storage units to define how much storage that you have. So instead of saying I have 1 million bits, you can instead refer to these possible names right here. And hopefully these are familiar to you. We have kilobytes, megabytes, gigabytes, and terabytes. So a kilobyte, if you guys remember, or if you guys have talked about the prefixes of these, like kilo, hopefully you guys have heard kilo before, like for example, in kilometer or in kilograms, it's the same kilo. It means 1,000, but it's not really 1,000 bytes. So when you see kilobyte, it looks like 1,000 bytes. It's actually 1,024 bytes, but it rounds to 1,000, which is why we call it kilobyte. The reason why we use 1,024 is because it's a power of 2. So we don't use actually 10 to the third. It just rounds to 10 to the third, but it's really 1,024. So 1 kilobyte is 1,024 bytes. We have 1 megabyte, which is 1,024 kilobytes. So it's like a hierarchy. And then we have a gigabyte, which is 1,024 megabytes. And then we have a terabyte, which is 1,024. Oops, this should not say terabytes. This should say gigabytes. Gigabytes. So a lot of you guys who have smartphones will probably have something around like, I don't know, like 256 gigabytes, maybe more, like 64 gigabytes at minimum, like 64 or like 128 or 256 gigabytes. So that's actually, that is 10 to the 9th, around 10 to the 9th bytes, which is a lot. If you are looking at a laptop or like a desktop setup, you could actually be looking at terabytes, which is over 1,000 times more than or 1,000 times more than a gigabyte. So we're dealing with so much data. When we think about data, it's not just about like a spreadsheet with a whole bunch of numbers in it. Data can come in forms of just numbers, text, pictures, video, audio, anything that is encoded into bits/bytes is considered data. So we're going to talk a little bit more about data today after we finish talking about the storage system. So we talked about how 1 byte is 8 bits, 1 kilobyte is 1,024 bytes, 1 megabyte is 1,024 kilobytes, 1 gigabyte is 1,024 megabytes, a terabyte is 1,024 gigabytes, and in fact, there's actually more than 1 terabyte. We have the petabyte, which is 1,024 terabytes. Rarely do we go into this realm. I don't think we have reached the time where everyone needs a petabyte at this point, but who knows, in the future, maybe this would be more accessible to the everyday person. As of now, I mean, even when I think about it, like when I was your age, I didn't have a flash drive that was like, or I think my flash drive was actually 256 megabytes when I was around 6th grade. And then all of a sudden it came to a point where everyone had, instead of megabytes, the flash drives were in the gigabyte realm. So, and then now we have terabytes, flash drives that are, that could store terabytes of data. But that was almost unimaginable when I was in 6th grade and then also in high school. So who knows, maybe in the future, everyone will have a flash drive that will like store petabytes of data. But as of now, it hasn't come to that point. So let's take a look at this question right here. If your phone has 64 gigabytes of storage, but my phone has 128 gigabytes of storage, how many more bytes do I have? So this is in gigabytes, 64 gigabytes, and then 128 gigabytes. But the question I'm asking is how many more bytes do I have? If we think about the difference in gigabytes, if I have 128 gigabytes and you have 64 gigabytes, that means there's a difference of 64 gigabytes in total. So 64 gigabytes, I would have 64 gigabytes more of storage because 128 minus 64 would give us 64. That's how I got that 64. So to convert it to the number of bytes, you're gonna have to do much more math. In fact, I think I just wrote it out because I didn't really want to calculate it myself, but you could see what we do here. 128 minus 64, we get that from doing the 128 that I have minus the 64 that you have, and that gives us the total number of gigabytes, or I guess the discrepancy of gigabytes between your phone and my phone. Now, if we think about the number of units that we have to go through, this is gigabytes, but we want to see what the difference in bytes are. So this is 1, 2, 3 different units that we have to travel through. And each one of these units, if you take a look, is a factor of 1024, which is the reason why I have 1024 to the third power, because each time I am calculating the converting from one unit to another, it's by a factor of 1024. So if you guys aren't convinced, I can show you guys a different way. Let's say I have 1 gigabyte. Let me change the color to green. Let's say I have 1 gigabyte, and I want to ultimately convert it into bytes. I can calculate or figure out how many gigabytes or how many megabytes make up 1 gigabyte by using the conversion factor that 1 gigabyte is the same thing as 1024 megabytes, which isn't what I want, but it's getting me closer to where I need to be, which is bytes. Now I'll convert the megabytes into kilobytes by converting 1 megabyte, which is equal to 1024 kilobytes. And then I can make that conversion one more time because I know that for each kilobyte, that is 1024 bytes. And by going ahead and doing this, I guess, kind of like fractional multiplication, the gigabytes will cancel out because the unit gigabyte is in the numerator and the denominator. The megabytes will cancel out because numerator and the denominator, and the kilobytes will also cancel out because numerator and the denominator. So ultimately what I have here, if I take a look, 1024, 1024, 1024, there's nothing left in the denominator, but in the numerator, I have 1024 multiplied 3 times, so to the third power, which is how we get to this. So that's another way of you thinking of it if you can't necessarily wrap your head around, like made 3 separate steps to get to a certain point. This would be your answer. For the AP test, you will not have a calculator, so you do not have to worry about these large numbers for the calculation. I don't expect for them to give you numbers this large for calculations. All the math that you have to do for the AP test, for the multiple choice of the AP test, should be able to be done with just a pencil and paper. This, I would say, is a little bit too large, so you don't have to worry about this math, but I do think it does get the point across about how this storage system works. Does anyone have any questions so far? Okay, so let's talk about our next part of storing numbers, and this is going to be using bits. So this is a little bit outside of the scope of the AP test, this part specific right here, but I thought I might as well just talk about it because it is, I would say, a topic of interest if you want to go into software engineering or hardware engineering, specifically hardware engineering. So remember the difference between software and hardware, just a little quick review. Software is like the computer programs, the things that you cannot physically touch within a computer, hence the word software. And then hardware is the more the tangible aspects of a computer. So the if you relate to like open up your computer, those things inside of your computer, that would be considered hardware. So for hardware engineering, this would be a little bit more relevant than I guess software engineering, but nevertheless, you should know it if you want to go to a higher level of computer science. So signed versus unsigned representation. So signed means that you have both positives and negatives. So signed means positive and negative, whereas unsigned means that everything is just positive. You don't have to worry about negative. So how you would represent if something is positive or negative using signed. Let's say I have the number 101. This number right here is called our most significant bit. It's a number pretty much at the very front. So this is the most significant bit. The number at the very front is called the most significant bit. The number at the very end is what we call the least significant bit. But what we're concerned about is the most significant bit, because that represents our symbol or our sign. If it's a 0, then that means our number is positive. If it's a 1, that means our number is negative. So because this number is a 1, if we convert it into decimal, it is negative. And then these two numbers right here represent the number itself. 0, 1 in binary is the same thing as just 1 in decimal. So this is -1 as a decimal number. This is a binary number. So this would be how you represent a signed number. If I have, for example, another example, let's say I have 0, 1, 0 as our binary number. So this is a signed, assuming that this is a signed number, I take a look at the most significant bit, that is a 0, so this must be a positive number. And then when I look at the number 10 as a binary number, 10 in binary is the same thing as 2 in decimal. So this is a +2 as a decimal number. So I believe that this right here is not within the AP test. You do not have to worry about it. Everything that you will be dealing with in binary numbers is going to be a unsigned number. So you don't have to worry about signed versus unsigned. You could assume that everything is an unsigned number in the AP test. However, I think it's just good to know. That way, if you guys are curious, like what about the negative numbers? This is how you would represent it, or sorry, signed numbers is how you would represent it in if you were to deal with negative numbers. Okay, so that being said, this is just an aside that I wanted to talk about, but let's talk about one issue that happens when we have a restricted number of bits or bytes. So we have something called overflow. The risk of overflow. Overflow is exactly what it sounds like. If you have a cup of water, or if you have a cup and you're pouring water in, if you pour too much, it overflows and you end up losing water because it will leave the cup. Similar concept, but with computers and with bits and numbers. So as an example, I guess this is a little bit misleading. So this right here is an example. It's not like an actual thing. The number, okay, yeah, this is just an example. So it's not a real concept. This right here, you have only 6 bits to represent signed integers. That is false. It's just an example. So in this case, in this example, what would happen if you ran this program? Let's go ahead and find out. X is equal to 15. We are going to convert this into a 6-bit number. A 6-bit unsigned number. So X is equal to 15 as a 6-bit unsigned number. If you guys don't remember how to convert, we're going to take the number 15 and then find its binary interpretation by dividing it by 2 each time until we get a remainder of 0. So we divide it by 2 because binary is base 2. So 15 divided by 2 is 7 with a remainder of 1. If it's divided by 2 again, I get 3 with a remainder of 1. But divided by 2 again, I get 1 with a remainder of 1. And divided by 2 again, I get 0 with the remainder of 1. So starting from here and working my way up, I have 1, 1, 1, 1, 0, 0. Because normally the number is just 1, 1, 1, 1. So 1111 as a binary number, but because I have 6 digits in total or 6 bits in total I need to occupy, I would just put a 00 at the very front because leading zeros have no meaning. It's like if I say 11, but instead of saying 11, I say 011. That's 11 to you guys. We're going to do the same thing, but with the number 20. So 1, 2, 3, 4, 5, 6. So when I try to find the binary interpretation for 20, let's use this color. So I divide it by 2. 20 divided by 2 gives me 10 with the remainder of 0. Dividing it by 2 again, I get 5 with the remainder of 0. Dividing it by 2 again, I get 2 with the remainder of 1. Dividing by 2 again, I get 1 with the remainder of 0. Dividing by 2 again, I get 0 with the remainder of 1. Starting from the bottom and working our way up, we get 1, 0, 1, 0, 0. So if I place this inside my binary number, like if I go ahead and rewrite it using the bits tab available, I get 1, 0, 1, 0, 0. And it's not showing up. So this is how we would add the two numbers. Or no, this is how we would represent the two numbers. Now we're going to add the two numbers. So x plus y, when I add x plus y, this should give me 35, right? 20 plus 15 is 35. So let's see what happens when I try to represent 35 as a 6-bit number. So I'm going to take, I guess I'll do the math over here on this side. So 35, and I'm going to divide it by 2. So 2, divided by 2, I would get, let's use red. So dividing it by 2, I would get 17 with the remainder of 1. Sorry, it's not showing up. There we go. Let me know if I'm cutting out. I divide it by 2 again. I get 8 with the remainder of 1. Dividing by 2 again, I get 4 with the remainder of, if I divide it by 2 again. Sorry, I'm waiting for this to catch up with me before I keep doing the math. I get 2 with the remainder of 0. If I divide by 2 again, I get 1 with the remainder of 0. And if I divide by 2 again, I get 0 with the remainder of 1. Starting from the bottom and working our way up, we get 1, 0, 0, 0, 1, 1. One, 0, 0, 0. Oh, this was a bad example then. 2, 4, 6. This is a bad example on my part. So 1, 0, 0, 0, 1, 1. Okay. So this is how you would normally do bit. Like this is how you would store number using bits. Let's say, however, instead of 6 bits to represent a number, you only had 5 bits. So as a separate example, you only have 5 bits to represent this number. Then this number right here would be 2, 3, 4, 5, 0, 1, 1, 1, 1. This number right here would be 2, 3, 4, 5, 1, 0, 1, 0, 0. What's the issue here if I try to encode this using only 5 bits? What's the issue with this one right here? It's too long, right? There's too many bits. So what would happen here? 1, 2, 3, 4, 5. The last 5 numbers would be fine. 1, 1, 0, 0, 0. However, there is overflow. So we lose the very first bit of our sum. So this right here, this is what we call overflow. sometimes you do have a risk of overflow when you're storing numbers using bits, which is why we have different data types. So if you guys remember in Python, we had integers. We also had float data types. So when it came down to the numbers, integers are normally represented in 2 bytes. So meaning you have 16 bits, right? Because 1 byte is the same thing as 8 bits. So you have 16 bits usually for integers. Floats are normally much more than that. It kind of depends on which programming language you use, because C++ and Java, they use doubles and then they also use floats. So their floats are actually much bigger in terms of size. And then we have Python, which also uses floats as well. But in general, floats are represented in more bytes than integers are. So integers are normally restricted to around 2 bytes. I would say floats are normally 4 to 8 bytes, which means you have much more storage, which also means that you can hold longer and bigger numbers when you are representing floats than when you're representing integers. There is a higher risk of overflow when you are using integers, simply because of the fact that your integers are have less space in it. And you guys just saw that firsthand here, that when we were trying to add 2 numbers, we were only using 5 bits as like a simple example, but you can see how a number became too large. You ended up losing the true meaning of the number because your bits would overflow out of the restriction of, or the restricted number of bits that you have. So that is one issue when you are storing numbers in bits. And in fact, it's not just numbers, it could be other forms of data, but typically you see this most in numbers. So does anyone have any questions so far? No? So I would say so far, the biggest takeaway from storing numbers using bits is, first of all, just like, the encoding of numbers. Know how to encode decimal numbers into binary numbers. And the second thing would be the risk of overflow. So overflow can happen when you are dealing with numbers that are too big in terms of, like, I guess, the size, compared to the number of bits that are offered for storage. So it's definitely a possibility. Next thing we're going to talk about is storing text in binary. So we talked about storing numbers. Now we're going to talk about storing text. So computers can store text in binary. And how we do it is mapping each character to a specific binary encoding. So here is my example of that. So we have the encoding, and then here is the text. For each set, or I guess for each encoding, we have a translation that it is mapped to. So if you see 0, 0, that means monitor. 0, 1 would be laptop. 1, 0 is floppy disk. I don't even know if you guys know what a floppy disk anymore. This is a floppy disk, by the way. That was, how old was I? I think I was like kindergarten when floppy disks were a thing. But it was like in an era before flash drives. And then 1, 1 is a keyboard. So if we take a look right here and split it up into 2 bits each, we want to encode this so that we know exactly what 1100011011 would mean. So 1, 1, what does 1, 1 mean? What would take the place, or what would actually represent 1, 1? What would 1, 1 represent? Oops. Yeah, 1, 1 is, it's a keyboard. I know it's a little hard to see, that's why I zoomed in. So the first thing that you guys would see is keyboard. So this right here would be keyboard. What about 0, 0? What would 0, 0 be meant to represent? Monitor, very good. So this would be monitor. What about 0, 1? Laptop, very good. And what about 1, 0? Floppy disk, yes. Floppy disk. And finally, 1, 1. Keyboard, very good. Doesn't seem too bad, hopefully. Makes sense, right? It's just literally, you're just given an encoding. It is mapped to a very specific text value. Whoops. So yeah, you guys can see the answer right here. So this is what it would be: keyboard, monitor, laptop, floppy disk, keyboard, because of how the encodings are set. So this is a very simple example of what actually happens. Hopefully you guys remember ASCII table from when we talked about strings. ASCII table is literally all about binary numbers. The ASCII table, so each character, I guess I could write notes here. Each character is associated with a 7-bit encoding. So for example, in the case of capital A has this encoding right here: 1 0 0 0 2 4. Wait, 1 1 2 3 4 5 6 1. So when you look at what is running in a program, or like what is running in a computer at this very moment, like what A is, you would not see the letter A. Instead, you would see this: 1 0 0 0 0 0 1. That is what you would see, which is why when we think about high level programming languages versus low level programming languages, it's very different. Just as a quick review, I kind of noticed a lot of people missed this question. I briefly talked about it a couple weeks ago, but high level programming languages is languages that you and I would use to program. So Python, C++, Java, all of these are high level programming language where you would type, where you would actually use the letter A. Whereas low-level programming languages are things that are more closer to the machine, so closer to the computer. So machine language, that would use more of this. So instead of using A, you would use 1 0 0 0 0 0 1. So very difficult to debug machine languages, very difficult to, I guess, use low-level programming languages. You are more inclined to use high-level programming languages and use an interpreter to change it into a lower level machine language or a lower level programming language. So just keep that in mind. We're not going to talk about low level programming languages. Just know what they are. And that's like all that you will be expected to know. So that being said, another disclaimer about this. Technically, 1 character is 1 byte. 1 character is 1 byte. But as you guys can see here, the largest number of bits that are being used is 7. So let's zoom in. We can see that this is 1, 2, 3, 4, 5, 6, 7 bits. But we know that we know 8 bits. 8 bits is 1 byte. So there's a little bit of a discrepancy here. 1 character is supposed to be 1 byte, but why is there only 7 bits maximum for these characters? This is because one of the bytes or one of the bits is what we call, oh shoot, what do we call it? It's like a checker. It's so normally we have 1, 2, 3, 4, 5, 6, 7, 8. This right here would represent the ASCII character. This right here is normally just 0. It's like a checker. It's a bit checker. So in total, all of this together would be 1 byte or 1 character. So don't be fooled. Don't think that because there are only 7 bits being used in the ASCII table that there's only 7 bits required in order for you to represent 1 character. Technically, it's 8 bits, not 7, okay? So 1 byte is 1 character. 2 bytes is usually an integer. You don't really have to know. You don't really have to know too much about like how many is like necessary. It's just that this is normally what happens in a computer. So 1 character is encoded by using 1 byte. If you guys notice, there's not a whole lot of characters here. Like for example, if you guys want to use Greek letters, or if you guys want to use other symbols that are not in the ASCII table, there is another thing you guys could use called Unicode. What's going on here? Unicode. That's the U. It's a Unicode. So Unicode is kind of like ASCII, but there's so many other characters in Unicode. I don't remember exactly how many because it's a lot, but Unicode consists of other characters from different languages. So you will also see Greek letters. There's a whole bunch of mathematical symbols also in Unicode. So if the ASCII table is not enough for you, normally ASCII table is enough for the purposes of the programming that you guys will do. Unicode is also an option, which has a lot more characters. I don't remember the exact number, but this right here will be encoded in more than 1 byte because there's so many more options in terms of the number of characters that there are within Unicode. So normally ASCII should be enough, I would say. So character encoding is going to be very similar to numerical encoding. It's just that after you have to map it. It's kind of like a match, literally like a code. So if you get a number, you have to find that number and see what character it represents. For example, here, if we take a look at, oops. So if you take a look at what we have, S, capital S specifically. Capital S here is represented by the decimal number 83. The decimal number 83. And really, technically, a binary number of 1010011. So what you see is the capital S. What the computer sees will be the binary number. Or is it 1010011, I think. This is what the computer will see. I guess technically 0 in front of that because we're using ASCII. When we see P, lowercase p, and we take a look at ASCII, if we find lowercase p, which is over here, lowercase p, that has a decimal value of 112 or 1110000. So if we take a look at what it says here, it would say 01110000. If we take a look at the R, so R, we look at where R is over here, which is decimal number 114, or the binary encoding is 1110010. So what it would say here is 01110010. And then you would just keep going. So this is how text is stored in a computer. Each one of these right here is one address, because each address is 1 byte. And we can see clearly that 1 byte, meaning 1 character, is being stored in each one of these addresses. Any questions? So we would have just like a whole bunch of just like literally a chain or like a storage unit of all of these. Cool. So things to take away. So you guys hopefully after like the end of like talking about binary and like hexadecimal and octal and like this entire PowerPoint, you're able to understand why binary numbers are important, why hexadecimals are important. Octal numbers are also important, but um, typically it's much easier to change binary numbers to hexadecimal numbers because binary numbers are so small. You could only use 2 digits, 0 or 1. So to make it into a number that's more easily understood, you want to use something with larger digits. Hexadecimal has larger digits. You could use from 0 all the way up to the letter F. So hexadecimals are important because it creates a more easily understood value than binary numbers would. Although to be honest, decimal numbers I would say are still the most important because that's the numbers that you and I understand. But for computers, powers of 2 because binary. That's the reason why hexadecimals are important. You should also have learned how to convert between number systems. So binary to octal, binary to decimal, binary to hexadecimal, also decimal to binary, decimal to octal, decimal to hexadecimal. So like those you should have hopefully learned. Also, units of storage measurement. So remember, bytes are like bits, bytes, kilobytes, megabytes, gigabytes, terabytes. Those are also going to, you also need to know how to do that. And also how to store certain kinds of data. So numbers, we talked about numbers, storing numbers as bits. We also talked about storing text as bits. We talked about the advantages of storing numbers as bits, but also we also had the risk of overflow. So that's also something that you want to think about. And once again, we also talked about ASCII just earlier, where we encoded and we could also decode numbers just based on code or like a binary code. Before we move on to the next, hello, did it freeze? Okay, before we move on to the next PowerPoint though, let's do a quick review question. How many bits are required to store the number 150 in ASCII? So notice that there's quotation marks. Quotation marks. When you see quotation marks, what data type is it? What kind of data type is it if you see quotation marks around something? It's a string. It's a string. So this means you are dealing with characters, meaning ASCII. So how many bits are required to store the number 150 in ASCII? Let's actually do a quick poll on this. Let's see. And all right, you guys should be able to see it. How many bits are required to score the number 150? I'm gonna wait for some more of you guys to vote. I'll give you maybe like 15 seconds, 15 more seconds to try this. Okay, so let me go ahead and send out this poll. So it's interesting. Let's see what the correct answer is. It was D. So remember, every character is 8 bits. There are 3 characters in total, right? 1, 5, and 0. So 3 times 8 should have given you a grand total of 24. That's the reason why your correct answer was D. I don't know if oh, okay, yeah. So the correct answer was D. So Good job to those of you who got it. All right, let's go ahead and then start the next PowerPoint. Give me 1 second to get to open that up. And okay, well, I was supposed to go over this last week, so that's the reason why the date says Tuesday. Whoops. This is because it was supposed to start last week. So let's talk about more about data. So data is always being generated by sensors, mouse clicks, camera shots, recordings, anything, pretty much everything that you do on a computer is almost always generating some form of data. Even when you're driving, a lot of like cars have some sort of software built into it now, you're generating some kind of data. When you are on your phone, you're generating data. When you take a picture, you are literally creating an image, you're generating data. Everything, like you are living in an age of information and data. We've discussed some forms of data already. We've talked about numbers and text. Now we're going to talk about 2 other forms of data specifically. Oops. So the next form that we are going to talk about, or we're going to focus on, is going to be images. This is going to be our point of focus for this PowerPoint, how we can represent images as data. We already talked about numbers and text. Those are not too bad. It was generally pretty straightforward because we already knew how to convert numbers, and also because we already have introduced the ASCII table. But what about images? Images have colors in it. Images have pixels in it. How are we going to interpret images as data? This is what we're going to talk about. We're also going to talk about, are we going to talk about it? Okay. We're also going to talk about how we can store larger images. So these images, generally, the sizes are huge. If you guys try to email something, sometimes maybe you guys might have realized when you try to email something, the data being stored is too large. So what do you do in those kinds of situations so that you can minimize or like decrease the amount of storage your data takes up? Those are the topics that we will be talking about in this PowerPoint. Let's see how much we can get through in 5 minutes. But overall, everything that we talked about is that, or everything that we talked about is rooted in binary numbers, literally as bits. So essentially images, those are binary numbers, those are bits. And it's kind of fascinating how just zeros and ones can allow us to do so much on a computer. But let's go ahead and talk a little bit more about data. So how data can be processed. Know all 4 of these concepts. Data is, once again, like I've said before, we're living in an age of information and data. If you don't know how to, like you've done some kind of data processing before, I guarantee it, especially if you've taken a science class, you have had to analyze your data. And that is all part of computer science as well. Different things that you can do with data. You can clean data. So removing corrupt data, removing or repairing incomplete data, and verifying ranges or dates. So let's say you're doing a science experiment and you realize that there's some kind of irregularity in your data and you're like, oh, this is weird. There must have been something wrong with this. You can remove that from your data in order for you to have a more balanced and recognizable data set. That would be an example of cleaning data. It's not super computer science related. However, this is still a concept that you have to understand if you want to be successful with like data processing and computer science. We have filtering data. So identifying and extracting different subsets to help people make meaning of the data. So if you are doing a study and you're trying to see if like maybe age has something to do with it, you can filter it by age. You can see like maybe ages like 5 to 7 versus ages 7 to 9, if there's any kind of difference with that data. That is an idea of filtering data. That way you can have a better idea of a smaller subset of your data rather than looking at a very large picture created by your data. Classifying data is another thing. So grouping data with common features and values. It's kind of similar to filtering, but normally classifying is trying to understand like, is it is based on your data, is it one thing or is it another? So a very classic example is it a husky or is it a wolf? You can be presented two pictures or like many pictures, and then you would have to classify it. Is it a husky or is it a wolf by looking at the features of that picture? So that would be classifying, whereas filtering is kind of based off of like separating the data as opposed to, or is separating into different subsets as opposed to classifying, where you are analyzing the data and moving it into different subsets. I don't know if I just confused you guys. Filtering is based off the data itself. Classifying is using the data to create your own conclusions, I guess. Patterns. So identifying patterns in data that people are either unable to recognize or cannot process enough data to see the patterns. So actually a lot of what I do currently right now in terms of my own research has a lot to do with data. It's handling large amounts of data and then trying to make meaning of it. And also trying to see if my program is able to uh, learn from the data without me specifically teaching it. So it's like literally artificial intelligence and machine learning. So um, this is all too familiar to me. Looks like we're running out of time. So next week, we'll pick up from here, and then we will talk a little bit more about image data. So we are going to be doing this kind of stuff. I was going to send out homework today, but homework did focus on images. Do not do the image part of the homework because we haven't talked about it yet, but you should be able to do the first part of the homework, which we did talk about. I will also be sending out another quiz for today, so I highly recommend that you guys take that quiz, especially because the AP Computer Science Principles test it's still like 3 months away, but you want to be exposed to as many questions as you possibly can at this point. And also keep an eye out for that packet I'll be sending out hopefully by next week, and then start on it. Do not fall behind, otherwise you're going to regret it when the AP test comes closer.